So, I will make use of this particular equation saying that flexibility and stiffness are crossed to become identity matrix, flexibility and stiffness matrix when they multiplied I get an identity matrix because one is inverse of the other. If I say delta Jj, delta Jk, delta Kj and delta Kk are the flexibility coefficients for jth and kth nodes. If we multiply this with P, Q and P Q, which are stiffness coefficients, which is KPP, KPQ, KQP and KQQ, I will get an identity matrix which is 1 0 0 1. Friends, please understand, my job is to evaluate this matrix. Okay. So, this matrix, if I call this as let us say A matrix, I can evaluate A as B inverse of I. So, I am now going to evaluate the flexibility matrix or the flexibility coefficients, invert that matrix to get my A matrix. Okay. So, let us do that now. So, the job is to determine the flexibility coefficients to derive the rotational stiffness coefficients, correct. That is our task now. Okay. Let us do that. So, let us take a beam which is simply supported. Let us give unit rotation to this end. Okay. Delta Jj of the ith value. So, let us impose theta j is equal to 1 and I get delta Jj, and this value will be delta Kj of the ith member. Okay. Let us call this as figure 1. Let us draw the next figure. Let me give unit rotation at the kth end now. So, the beam will deflect in this manner. Let us say these are my rotational coefficients delta Kk and delta Jk. Let us call this is figure 2. Equivalently, let us try to draw the beam with this end fixed, but this end rotated, with KPP imposed, which will cause KQP for theta p as unity. I will call this as figure 3. Similarly, let us say this end is fixed and this end is imposed by a rotation, which is going to cause QQ, which will cause an end moment KPQ, and that is going to cause a rotation of theta q, which is unity. I call this as figure 4. Let us refer to these 4 figures and understand what we have done in these figures. Figure 1, we have given unit rotation at the jth end. Figure 2, unit rotation at the kth end. Figure 3 is the rotational coefficients caused because of that rotation at jth end and kth end respectively. So, now we can straight away say figure 1 and 2 shows the flexibility coefficients delta Jj and delta Kj define rotations at n, j and k respectively of the ith member caused due to unit moment. Okay, we are talking about flexibility. So, unit moment applied at jth end, correct. Similarly, flexibility coefficients delta jk and delta kk define rotations at jth and kth ends of the ith member due to unit moment applied at kth end. You can see in this figure unit moment applied at jth end and kth end will give you the flexibility coefficients respectively as you see in figures 1 and 2. Similarly, the stiffness coefficients Kpp and Kqp define end moments that is required at j and k ends to maintain equilibrium when jth end is subjected to unit rotation while kth end is restrained. You can see here this is unit rotation, but kth end is no rotation, restrained. Okay. Similarly, stiffness coefficients Kpq and Kqq, that is Kpq and Kqq of ith member define end moments required at j and k ends to maintain equilibrium when kth end is subjected to unit rotation and jth end is restrained. You can see in this figure jth end no moment, no rotation, kth end is subject to unit rotation. Okay. Having said this, let us now establish the fact that j k and j k. So, I should say the flexibility coefficients j j, j k, k j, k k multiplied by the stiffness coefficients k p p, p q, q p, q q will give me identity matrix. Let us expand this. So, k p p into j j plus k q p into j k is 1 and k p p delta k j plus k q p delta k k is 0, that is this row multiplied by this column is 0. Okay. K p p delta k j, k q p delta k k is 0. Okay. This is one set of equation we have. Similarly, k p q delta j j plus k q q delta j k is 0. That is this by this is 0. Okay. Then k p q delta k j plus k q q delta k k is 1. The second set of equation we have. Okay. Now, I call this matrix as flexibility matrix, I call this matrix as stiffness matrix, I call this matrix as identity. The subscript R stands for rotational degrees of freedom. Okay. Now, my job is to estimate the matrix dr. So, now to estimate the matrix dr, okay, for the beam element. So, once we get that, we will be able to find the Kr. So, let us do that quickly. This is my beam, this is my deflected shape, I cause unit moment and this value is going to be delta j j and this value is going to be delta k j of the ith member. Okay. So, if this is m, we all know that there is an anticlockwise moment which will be balanced by a clockwise couple which will be 1 by L and 1 by L, where this is L. So, let us try to draw the bending moment diagram for this. So, this value is going to be 0 here, this is going to be 1, which will have tension at the top and compression at the bottom. Okay. So, let us now replace this loading diagram with a conjugate beam. The conjugate beam will have a loading diagram as I am drawing now, which will have 1 by E I as the loading diagram. So, this is going to be 1 by E I, okay, and this will remain as simply supported. So, I call this moment as A, let us say the point A, take moment about A, okay. So, I call this as B, therefore, the reaction is VB. So, I should say VB straight away is half Li, that is my distance, and 1 by EI, that is my height, and the moment is going to be 1/3 of Li. Okay. I have to divide this by Li again to get my VB, where my VB will be in the reverse direction, which will be actually equal to Li by 6 EI in this direction. So, I mark that value here, which will be Li by 6 EI. Okay. Therefore, VA will be actually half Li 1 by EI minus Li by 6 EI, which will give me Li by 3 EI, which is upward. So, this value is going to be Li by 3 EI. Similarly, one can do for the other case and see that this matrix is derived simply as L by 3 EI minus L by 6 EI minus L by 6 EI and L by 3 EI. Okay. Therefore, Kr will be actually dr inverse, which will be actually equal to 1 by determinant of L square by 9 EI square minus L square by 36 EI square of L by 3 EI and L by 3 EI minus 1 cube of minus L by 6 EI minus 1 cube of minus L by 6 EI, which will amount to 12 EI square by L square of L by 3 EI, L by 3 EI, L by 6 EI, L by 6 EI, which will be actually 4 EI by L, 2 EI by L, 2 EI by L and 4 EI by L. So, now this is similar to PQ, which is 4 EI by L, 2 EI by L and 2 EI by L and 4 EI by L. So, friends, once we know this PQ, the remaining matrix can be taken as seen from this equation. So, if I know these 4, remaining all can be computed. Now, I am writing the full matrix, which is very easy to remember. I am writing the full matrix of the ith member, which is P, Q, R, S, which is P, Q, R, S. The 4 values are 4 EI by L, 2 EI by L, 2 EI by L and 4 EI by L, which we derived just now. Okay. I wrote that. So, this will be, this value will be the sum of these two by L again. So, 6 EI by L square, this is negative 6 EI by L square. This value will be sum of these two by L again. So, 6 EI by L square, and this is negative of that value 6 EI by L square. This value will be sum of these two by L again. So, 6 EI by L square, this will be sum of these two, which is 6 EI by L square. Now, this value will be sum of these two by L again. So, 12 EI by L cube minus 12 EI by L cube. Once I get this, the last column will be reverse of R column, which is minus 6 EI by L square minus 6 EI by L square minus 12 EI by L cube and plus 12 EI by L cube. So, friends, as a summary we can see here. So, I can write this as a simple summary we have for the beam element. If I am able to compute these 4 coefficients, I can find the remaining 12, which is comprising 4 by 4 of rotational matrix of the ith beam, which has got 16 coefficients, which are derived based upon only the 4 coefficients of rotation. Thank you very much.